Okay, great. Okay. Well, thanks everyone for being here, and special thanks to Martin Rasmussen from Imperial College London for agreeing to give a talk. Um, his research is typically in quantitative theory of non-autonomous and random dynamical systems. He touches on stability and attractor theory, bifurcation theory, theory of invariant manifolds, and Morse decomposition theory. So all things that this group is typically interested in. So I'm really looking forward to this talk. So today, Martin will talk on transit times for non-autonomous compartmental systems with applications to ecology. And with that, I'll let you take it away. Thanks.
Thank you very much, Christian, for the nice introduction. And thanks also to Emmanuel for inviting me to give this presentation. So my talk is about transit times in compartmental systems. So compartmental models play an important role in the modeling of ecological systems, and we are mainly interested in the terrestrial carbon cycle in this talk. And the work I would like to present concerns transit times and was done in a working group of ecologists and applied mathematicians. The activities of this working group were funded by NIMBIOS, which is the National Institute for Mathematical and Biological Synthesis. And we were meeting in Knoxville about, I think, 4 times for quite a few number of years ago. And here you see a picture of our last meeting. And this was a very enjoyable time to work with this group. And the first part of this talk concerns outcomes of this working group. And after the working group finished, I continued to work together with Alan Hastings and Chappelle on transit times. And we obtained a bit more refined results. And also we considered a different application given by breeding stages of the Southern Fulmar bird population. So this will be towards the end of the talk. So what is the terrestrial carbon cycle? So basically the idea is that carbon is stored in different parts of the system in different pools. So there are plant pools, litter pools, and soil pools, and carbon can move between these pools. So plant pools, for instance, also concern wood and roots. And so typically carbon moves from plant to litter pools, which are leaves, and then you move to soil pools. And this is only hierarchically possible. Of course, you cannot really go back. And carbon is also exchanged with the atmosphere, and carbon in particular moves into the system via the plant pools only. And so the main question in this talk I would like to address is what is the transit time of the terrestrial part of the carbon cycle, which is given by this part of the carbon cycle here. So this means what is the average time carbon stays in the terrestrial part of the system? And that is, of course, a very important question because due to global warming, the chemical processes related to these transitions, they accelerate. And so carbon cannot be stored as long as it used to be stored in the terrestrial part of the carbon cycle. And we would like to understand more about this typical time and how to quantify this time using mathematical theory. And so the perhaps simplest way to model such a compartmental system is given by a linear autonomous compartmental system. So this is basically a linear inhomogeneous differential equation. So you have a coefficient matrix B, and you have some inhomogeneous part S. So the inhomogeneous part, which is given by this vector S here, models the mass coming from outside. So each of the components of this vector is non-negative. And then the coefficient matrix B describes how carbon is decays and how carbon is redistributed in the system. So the diagonal elements describe how mass is decaying in each pool. So we have exponential decay. And this mass either leaves the system or is redistributed to other pools. So the green elements in this matrix describes how mass moves between the different pools in the system. So this is positive, and we cannot allow mass to be created. So when we take the sum over all elements in a column, then this has to be non-positive because otherwise mass would be created. So let's maybe look at a very simple example. So we have here a two-dimensional autonomous differential equation with some inhomogeneous part. And so this means that 3 units of mass per time come into the system. 2/3 of this mass goes into the first pool, 1/3 goes into the second pool. The first pool has a decay rate of -2. And because we have 1 here, this means that 50% of the mass that decays in pool 1 is redistributed to pool 2, and the other 50% leaves the system. Then in the second pool, we have the exponential decay rate -1. And because we have 1 here, this means that all the mass that decays in pool 2 gets redistributed into pool 1, and no mass escapes the system from pool 2. And so this is a very simple scenario. So when we impose very mild conditions, so that mass cannot be trapped, one can, in particular, that you don't have cycles. So for instance, when you would have -1 here instead of a -2, then you would have cycles, so mass cannot leave. But if you make sure that mass always can leave, then the matrix B is invertible, and the real parts of the eigenvalues of B are negative. So we are in an asymptotically stable situation, and we have a unique equilibrium, which is given by -b to the -1 times s. And so this is the equilibrium state of the system and will be approached exponentially fast from any other state. And let's now consider the question of the transit time. So we would like to understand how to compute these times. And this is in particular relatively simple for a one-dimensional system. So here we have a one-dimensional autonomous compartmental system, a decay rate B, which is less than 0, and some input from outside. And to understand how to compute this characteristic time, we just consider that we have some mass in this one pool system given by 1. So we have an initial condition, and we somehow just look at how the mass decays. And of course, this is explicitly solvable. It's a linear autonomous system. So the solution is e to the b times t. And then we get immediately this distribution function of mass that has left. So this is given by 1 minus this solution. And when we take the derivative of this function, we get the density of mass leaving the system. And then we just have to calculate the expectation of this probability density, and we end up by a simple integration with -1 divided by b, which is the average time mass spends in this one-dimensional compartmental system. And so, of course, this makes completely sense. So if b is very small, the decay is, so if b is very close to 0, but negative, then there's almost no decay, and this characteristic time will be very large. But if b is very, very negative and far away from 0, then this time will be very, very small. And let's now look at a higher dimensional system, at a two-dimensional system, and let's use this one-dimensional knowledge how to calculate this characteristic time. And so the calculations can be done in general terms, but I run you just through this example, but you see also how this calculation work in a more general situation. So we just take this example, which I have used before to explain the compartmental system. And now we just think about this whole situation as follows. So if mass is in pool 1 or comes into pool 1, then it spends, because we have a decay rate of -2, then it spends the mean time 1/2. So this is the formula we have calculated before in pool 1. And then it gets redistributed either to pool 2 or it leaves the system. And because we have with 50%, it goes to pool 2, and with 50%, it goes outside. Now, when a particle comes into pool 2, situation is slightly different. So we spend the mean time 1 in this pool, and then we are not allowed to go out because this gets redistributed only to pool 1. So with 100% probability, we go into pool 1. And now let's look at the following quantity. So we look at Ri, which is the average time in the system for a particle that has entered pool I. And we do not distinguish whether we come from outside of the system or we come from another pool. So once a particle goes into the pool Ri. We want to calculate the average time the particle is in the system. And so this satisfies clearly these two linear equations. So say a particle comes into pool 1, then what is the average time that it spends in the total system before it leaves? Well, it first spends time 1/2 in pool 1, and then the probability, so with probability 1/2 we go outside, so we don't have to count this, but with 1/2 probability we go into pool 2, and so we spend an additional 1/2 times R2 in the system. So this is one part of the linear system. The other part is when we look at pool 2. So R2, this is the time that we spend in the system when we move into pool 2. And so we spend on average 1 time unit before we either leave or are redistributed to another pool, but here we are redistributed to pool 1. So we enter pool 1, so we have to add here just R1 at the time that we spend in the system once we enter R1. So we get a linear system. Here, a two-dimensional system, two equations. We can solve this, and we can immediately calculate these quantities. And I note that the matrix inverse plays a role here, and that also holds in more general, higher dimensional contexts. So we get basically that if we move into pool 1, we spend on average 2 time units into the system, and if we move into pool 2, we spend on average 3 time units in the system. And now from outside, we come with different, so 2/3 of the particles go into pool 1. So we have to basically take 2/3 times 2, which is the time, which is this time R1, which is the time you spend in the system when you move in pool 1, plus 1/3 times the time you spend when you move into pool 2, and then we get a transit time of 7/3, which basically describes the situation very accurately here. And so in general, as I said, so the matrix inverse plays a role. So we basically so we look at what is the probability to come from outside into the system. So this is the probability vector beta, which is here given by 2/3, 1/3 in this example, and we multiply this with b to the -1, and then sum up all the entries of this vector, and then we get the transit time in the general higher dimensional autonomous case. So that's quite interesting. So when I first saw this, actually I've never really seen a proof in the literature of this result, but with our non-autonomous theory, we proved this formula directly. But the remarkable thing is that for a linear system, that the matrix inverse plays a role here. So this is kind of intuitive if you understand a little bit more about that, but that was a little bit of a surprise for me when I first have seen this. And then there is also a more refined result possible. So the question is not only how much time do I spend into this in the system when I move into certain pools, but the time is how much time do I spend in different pools when I move into a certain pool. And this is exactly all described by the coefficients of the negative matrix inverse. So each entry of the matrix inverse has the meaning of a characteristic time. And basically, the entries in the ith row and the jth column is the time spent in pool I of a particle coming in pool j. So if we sum up these Cij's with respect to the index I, so if we take the sum over the columns, we get to our characteristic time Rj, which we have calculated for this two-dimensional example before. So that's a very, very nice result. And now this is just the background information. So this is basically what was known when we were meeting with this working group. But of course, the terrestrial carbon cycle is a non-autonomous system. In particular, as I have highlighted before, chemical processes speed up these transition rates and speed up also the way the carbon gets released into the atmosphere. And also we have non-autonomous inputs coming from a non-equilibrium state of the climate system, basically. So so we have to basically move to a more complicated model, which is given here by a linear non-autonomous compartmental system. So basically all the coefficients in this matrix B and also all the entries in this input vector S, they are allowed to depend now on time. In order to get a compartmental system that describes movements of mass, we also need to impose exactly the same conditions on these coefficients, just that these conditions hold now for each t. And so this describes basically the situation in the non-autonomous context, which we need to model this terrestrial carbon cycle with these type of models. And this is a much more complicated situation because when we have a non-autonomous linear system, we cannot even solve it. And also we cannot deduce stability from just looking at the eigenvalues of the coefficient matrix B of t. So there are known examples where the eigenvalues can be all negative, but the system can be unstable. And so, but nevertheless, when we are in our situation of a terrestrial carbon cycle, or when we are in the situation of a compartmental system where mass cannot get trapped, and one has to formulate this appropriately in this non-autonomous setting, what it means. But if this is the case, then there exists a solution x star of this linear differential equation, linear inhomogeneous differential equation, that is globally attractive in two different senses. So this means that any other solution in a certain sense converges to this attracting solution. So in two different senses, I mean with respect to forward or pullback attraction. So these are two different types of attractions that you find in non-autonomous systems. And the reason why we have two different ways to formulate attractivity is that, so attractivity means attraction over an infinite time interval, but for non-autonomous systems, we can either fix the starting time and go towards infinity. So we get an infinite time interval. So basically here, for the forward attraction, you would fix the initial time t0, the initial state x0, and you let this solution look at the corresponding solution to this initial value problem and let time tend to infinity, and that would converge to this solution x star. So this is forward attraction, but alternatively, you could fix the time t0 and let the initial time go to minus infinity. And so this is called pullback attraction, as you start progressively earlier. Also, so that was wrong. So you fix the final time t, and you let the initial time t0 go to minus infinity for some initial state x0, and then in the limit t0 going to minus infinity, you converge to the solution x star at time t. So t is fixed. So this can be visualized here as follows. So forward attractive means we start with different x0 at a particular time t, and we converge forward in time to this x star. And so forward attraction describes clearly only behavior of the system in the future, because any information from the past is not considered in this definition. And pullback attraction describes the behavior in the past. And here this basically means that we start progressively earlier. So t0 goes to minus infinity. We fix some x0. We look at the corresponding solutions. We stop t solutions at time t. And in the limit t0 goes to minus infinity, this converges to the solution x star at time t. And so why have I put such an emphasis on these attractivity properties? Because we also have similar versions of transit time now. So we have transit times that correspond to the future of the system, and we have transit times that corresponds to the past of the system. And perhaps forward attraction is the most natural way to look at attractivity. So pullback attraction is something which is not so natural, especially for those who purely work with autonomous systems. And in that sense, a forward transit time would be also a natural form of transit time. So this would basically measure when you put a particle into the system at time t, it would basically measure what is the average time until this particle escapes the system. And so this is something I would explain towards the end of this talk. So the application for this would be when we look at breeder stages of the Southern Fulmar seabird population. But for the terrestrial carbon cycle, I would like to consider the pullback transit times. And there are very good reasons for that, why this particular transit time is more suitable for this application. I will say this in a moment, but let me first explain what is the pullback transit time. So here we would fix the final time, and we would basically look at the mean age of particles that leave at this particular time the system. And of course, because we somehow look at what happens at one time, and the whole history is important for this particular time, it only covers the behavior of the system in the past until time t. Now we know that climate models go into the future, but of course, so this time t is flexible. So this time t could be in the future, but we particularly do not want to let t tend to infinity, because then we basically don't know what our climate models are doing. So we go a little bit into the future, where there is reasonable modeling available. And then we basically would see how this mean age of the particles that leave the system at these particular times changes in time, and that would give an indication of how these quantities change over time. And this is our application of the terrestrial carbon cycle. Now we have to worry about these mean ages, and this means we have to, in the first instance, one approach would be to just look at the age distributions. So basically you can look at, so once a particle comes into the system, you can give an age to this particle. So depending on how long is this particle in the system, and you will get a distribution of ages. So this will be this quantity pi of a comma t. So this is a mass density function on the HA for mass that is in the pool I. So basically, if you integrate here over the ages, you will get exactly the xi, so the xi of t, so which is basically the component of the solution at time t. So this is a mass density function. And then we basically have to evolve this mass density function. So how does the mass density function evolve? So this is evolved by the well-known McKendrick von Förster equation. So this is not something very complicated. So you can just, in the first instance, forget about this term dpi over dA. Then you would see this is basically just the evolution of the differential equation. But now you have to also take this aging into account of the particles. That's why you have this transport term here. And of course, this is a PDE, so we have to worry about initial conditions. In particular, at time t, h0, you get the input from outside. This is the ice component of the input vector. And also we need to initialize the system at a particular time 0 or at another time, whatever you prefer, with some h distribution A. And then we can just run this McKendrick von Förster PDE. So this is not solvable. So in particular, because you have a non-autonomous system, because I explained to you the linear system is not solvable. And this is basically the same kind of complexity here. But we found a very nice solution to this, because we are not interested necessarily in the whole distribution of ages. We are only interested in the mean age of the particles that escape. So we just look at the mean age of mass that is in pool I, so this would be, we divide here by xi, and here we just weigh this integral with the h, so we get the mean age in pool I, and then you can take the derivative with respect to time of this ai of t, and then you will see after a few calculations that you end up with an ordinary differential equation. So this is very nice that when we restrict our attention only to the mean quantity and not to the whole distribution, that our PDE becomes an ODE somehow. So we restrict, of course, the information, but we restrict on the relevant information we want for our transit time. And so we get an ODE, and the right-hand side of this ODE looks like this, and this is the sum of 3 different components. So basically, a particle ages, so this is basically A dot is equal to 1, and then basically the H reduces depending on the input from outside. Of course, particles that come from outside via the input vector S, they have H0 when they arrive, so they decrease the H, and then we have basically mass exchanges from different pools in the system, and depending on whether the mean H in these different parts of the pools are larger or smaller, then the reference pool I'm interested in, the H increases or decreases, and this is exactly given by this ordinary differential equation. And that means that we have a relatively simple situation now. So we basically have a skew product dynamical system. So we have our non-autonomous differential equation that describes the masses of our terrestrial carbon cycle system, or of our non-autonomous compartmental system in more general terms. And then we can track these mean H's by an equation that now also depends on the solution of this X equation, but the X equation doesn't depend on this H evolution. And having this skew product system, we can basically look at the quantities we are interested in. We can look at the transit time. So this is denoted here by R of t, time-dependent non-autonomous quantity. And also we can look at the mean H at time t of all the mass. So what is the mean H of the mass that is currently in the system? So here, just remember, so this is just the mean H of mass, which you immediately see from this formula. But here we look at instantaneously what will be released, what is the H distribution, or what is the mean H of the particles that are released at a particular time t. So this is some instantaneous quantity that can change very wildly, very quickly, depending on how you change the right-hand side. And that's a bit more slow, because this is some kind of integrated quantity. So these are normally different. So even for autonomous system, the transit time is different to the mean H. But for one-dimensional systems, it's quite clear. So for one-dimensional systems, non-autonomous systems can be solved, and the mean H equation reduces to this. So we have basically just an Hing term, and we have a term that decreases the H depending on how much mass comes from outside. We can explicitly solve this, and we can immediately see that the transit time is equal to the mean H. Now let's, so maybe I can quickly ask, so this was the theoretical part. Are there any questions so far? Maybe time to quickly look at any...
Yeah, I have a quick question.
Yes, of course.
So then, did you say that the mean ages converge to the mass density function, or is it just the A? Was that the condition that you had? Was it the mean ages, or simply just
So you mean in this particular example, or
before, like
before?
when you said the condition, like in the Mac-Kendrick von Foster equations.
Okay, so the McKendrick von Foster equation is the...
Yeah, so you said let A. So this A here is just general. It has nothing to do with the...
No, this is, sorry, there's a little bit... Yes, it's somehow H, but it's in a different meaning. So this A here means mean H, and this H just means the H of the particles. So this is basically a distribution on the HA here. So if you integrate over A, you get the whole mass. And here it's the mean H. So that's maybe not optimal notation here. Thanks for asking. Maybe we should change for the next time we give this talk. Are there any other questions? So let's now look at the terrestrial carbon cycle. So we looked at the so-called CASA model. So here we have the plant pools, the litter pools, and the soil pools. And so here you basically see, so these coefficients, I don't really give all the numerical values here. It just shows you how the transitions work. So basically from the plant pools, you go to the litter pools, and then you go to the soil pools. And the autonomous version of this would be if this gamma of t is equal to 1. And for the non-autonomous version, gamma of t depends on time and depends in particular on the land surface temperature that is given by a function of time. And so basically this is So in this model, this gamma of t is monotone, or almost monotone, and increases in time, and speeds in particular the chemical processes up in the litter and in the soil part of the system. And here input only goes into the, as you see in the first three component, goes into the plant part of the system. And then we can do all the calculations. And you will see that here, so this would be basically, so we compare here, so this is the transit time, R of t. So here the non-autonomous quantity, and here it would be the autonomous quantity if you just freeze the system at a particular time. So this is of course not a relevant, this quantity doesn't have any meaning. It's just for illustration that if you naively apply the autonomous theory to just take your coefficient matrix, the inverse of the coefficient matrix at a particular time, you can calculate this quantity very easily by means of this matrix inverse, as I showed you at the very beginning of the talk. But this doesn't have any meaning because you basically, the system is changing all the time. So basically, the interesting thing is that at the time when we wrote the paper, we couldn't really explain this very well. I mean, it's a nine-dimensional system, but we see here this non-monotonic part, both for the transit time, but also for the mean ages. So mean ages are driven here mainly by the soil component. So the soil component, it has a very slow. So these coefficients here, this B77, B88, and B99, they are very close to zero. So the particles are very old. And that's why we have a mean age of 800 years, but we have only a transit time of around 43 years, which decreases actually quite well. So here we have to say, so time zero corresponds to 1850. So up to then, we assumed that the situation is constant. So we're basically an autonomous system until 1850. And then, so we are approximately here at 2024. So we are basically here somewhere. And so these times will still decrease according to this land surface temperature model, which we used, and quite significantly so. And yeah, so also here we have the instantaneous quantity, which has no meaning. But we see this non-monotonic behavior. And so this is something that puzzled us a little bit. But first of all, so I will explain this a little bit, how these non-monotonic terms can come into play. Of course, for this nine-dimensional model, it's difficult to explain. But we will see already for non-autonomous two-dimensional models how to create this, and we will be able to understand this. But first, I would like to look at a refinement of our result. So the question is now not only the transit time, the time spent in the whole system, but how much time is spent in each pool. And so here we can use the same approach as before. So we can use the mechanical contrastor equation, but we have to extend it somehow. So we have to basically look at a mass density function on the HA like before. But this H depends only on time spent in a certain pool. So we are basically here in pool I with this density function. If you integrate over, A and sum over K, we get the mass in pool I. But so this H here depends on the H only spent in pool K. And so we can then look at the extended version of the mechanical contrastor equation, where this transport term only appears in the diagonal parts. So the aging only takes place because here we basically look at, we are in the same pool where the clock ticks, and here the clock stops basically. That's why we have just a evolution like in the non-autonomous differential equation. And so this basically describes all these quantities here. This is of course now d squared dimensional, but nevertheless, one can do the same trick as before. One can look at a mean age equation by just looking at the mean ages described by these distributions here. Actually, if you sum over k, that would not really make sense. One has to do convolutions here to get this age distribution. So this pi from before would not be the sum over the pi case, where you sum over k, so we need to do some convolutions. But the upshot here is that you can come up with a mean age equation, which is an ODE like before, but it's just d² dimensional. And we have done this, but let's look just at a simple example to get a little bit of feeling for how this works. So here we have a non-autonomous two-dimensional system. So input comes into the first pool. And here we have a monotonic slowing down. So we have, of course, a negative coefficient here for the exponential decay, but we have an increasing function. So we slow down the decay. And so this is asymptotically autonomous. So if we look at minus infinity and plus infinity, we are almost autonomous. Yeah, asymptotically autonomous, we converge to an autonomous system. So for these autonomous parts, we can basically use the old theory. We can just take the autonomous theory. We can take the matrix inverse at minus infinity and plus infinity. And here we have to look, because we only enter into the first component, we only have to look at the first column of this matrix. So here, basically, this would mean the system at minus infinity behaves as follows. So if you put a particle into pool 1, you spend on average time 1 in pool 1 and time 2 in pool 2. And this, because basically the first pool is autonomous, so there's no time dependence, only the second pool is non-autonomous, and I cannot come back into first pool. This is the time is here the same, so this time wouldn't change. But because of the slowing down, our time spent in the second pool increases from 2 to 10/3. And now let's look at what, so this is basically these are basically the target values we would get. If we look at the non-autonomous time, we would actually expect so these times which are the proportions of these transit times, so would be basically R1 to RD, which would sum up to R of t. So these proportions, so the transit time here would be 3, and here would be like 1 plus 10/3. And so basically we see these transitions now, how they happen for the refined transit time. So here first we have the mean ages. So the mean ages are they are integrated quantities, so they just depend continuously. But here, the strange things we see here in these transit times, and so we see, even though everything is autonomous, everything is monotone, we see here non-monotonic behavior. And basically this can be easily explained why we get non-monotonic behavior. So here, the yellow graph is the instantaneous quantity, which doesn't have a meaning in the non-autonomous context. And the red graph is the non-autonomous quantity, depending for the time spent in pool 2 of a system that of a particle that comes into pool 1, because here we basically only come into pool 1 here, so this is fixed. And so this time decreases because we do the slowing down. So but there are two effects of doing the slowing down. So the first effect is that we no longer release so many particles from pool 2 because we slow down. And if we do not release so many particles from pool 2, this means that our instantaneous quantity goes down because more particles proportionally are released from pool 1. So pool 1 somehow dominates or gains some dominance. So that's why the average time spent in pool 2 goes down. But then because of the slowing down, we increase the mass in pool 2, and by increasing the mass in pool 2, we also increase the output in pool 2, and so the dominance will be basically given back to, in some sense, to pool 2, which is this lower pool. So we get much more particles coming out, and also the times will go up as a consequence. But we see this non-monotonic behavior, and we've seen this also in particular when we look at a more complicated system. You see more crazy behavior. This is just to illustrate that sometimes a little bit counterintuitive things can be observed, and in a higher dimensional system, it's often quite difficult to explain these things. So now, how does this look for our CASA model? So in the CASA model, most of the time is spent so here we aggregate over the different pools. So most of the time is spent in the soil part of the system. So this is approximately 30 to 25 years, so it decreases over time. What doesn't decrease over time is the time spent in the plant pools, but we have a non-autonomous effect at some point, because we somehow changed it because we have a higher dimensional plant model, 3-dimensional plant model, and this goes with different rates into a system which is outside of equilibrium and gets changed. So this has some effect on these times for the plant pool as well. But the least time is spent in the little part of the system. And here we see these decreases over time. And as I said, in the plant pool, there's no decrease because it is essentially an autonomous system. So in the last few minutes, I have, I think, 3 or 4 minutes left. I would just look at this forward transit time. So this I explain only roughly without mathematics. But so the idea is basically that if a particle comes at a specific time t into the system, it can stay until infinity, but of course it has to escape at some point. And then you look at the average time. So this was basically how we calculated for this one-dimensional system at the beginning of the talk. But here we have, a one-particle system. So this is, if we look at the Southern Fulmar seabird, and we look at, in particular, reproduction and breeding stages of the seabird. And so this can be modeled by a Markov chain. And so basically you can view the seabird in different stages or in different states, and then they can transition with certain probabilities to other states. So if a bird is born, then of course we are in a pre-breeder state. We haven't done any breeding attempt, but then you can move into either a successful breeding attempt or a failed breeding attempt, but you can never go back to the pre-breeder stage, because once you had some breeding attempt, you cannot go back. But from that, you can have further failed attempts and further successful attempts, but you can also go to a non-breeder state. But from the non-breeder state, you can also go to successful and failed. So this is basically the model, and there are probabilities involved. And where does it come? So the question is now, so I should maybe say this. So what we characterized as transit times before is the expected number of breeding attempts during the lifetime of a Southern Fulmar seabird. And so this is a non-autonomous problem because these transition probabilities, which are given here in this matrix, depend on time. And so the Southern Fulmar seabird lives in the Antarctica, and these transition probabilities depend on external conditions, which is given by the ice cover. So in this paper, they have basically looked at the ice covers and classified this into 3 different categories. So favorable, ordinary, and unfavorable conditions. They calculated in different transition probabilities. So actually, when you're in a pre-breeder state, it's very likely that you stay in a pre-breeder state, and many birds die before they actually have some breeding attempts. But once you have either an unsuccessful breeder attempt or a successful breeder attempt, you actually are in this part of this system here, so in states 2, 3, and 4, and it's much more likely that you produce further offspring. But nevertheless, so this is a non-autonomous situation. So you can either run the standard theory, like I explained it at the beginning. Of course, this is here for Markov chains, so this is analogous in some sense. So this is not a differential equation, but the formulas are analogous in some sense. So you can calculate the transit times, which corresponds to the number of offspring, using these matrices. But you can also look at the non-autonomous situation. And we looked here, we compared this. So we have basically autonomous theory for constant, favorable, ordinary, and unfavorable. When we look at certain initial stages, so initial stage pre-breeder, so say that if everything is unfavorable, if you're in a pre-breeder state, it's very unlikely that you have some offspring. But nevertheless, under the time varying and under this realistic scenario, you have 2 offspring according to this model. But once you are in one of these other 3 stages as an initial condition, you have much more successful breeder attempts. And basically, the message is that you cannot really use this autonomous theory because the conditions change over time. And for this particular historical time evolution, which was discussed in this paper, we get a characteristic transit time, which corresponds to the successful breeder attempts for different initial conditions. And these are relatively close to the ordinary, if you just assume that everything is constant ordinary. But nevertheless, because this situation is non-autonomous, we need basically a non-autonomous theory to be able to cope with this situation in an appropriate way. So let me conclude now. So we looked at transit time for autonomous compartmental systems first, and so I explained how to obtain explicit formulas, which are really simple. And basically the matrix inverse of the coefficient matrix P, all the characteristic times are included. But we need a non-autonomous theory, and this is a little bit more complicated. So we looked at two different ways to do it, for forward times and for pullback times, and both have their meaning for different types of applications. And we considered both the terrestrial carbon cycle and the breeder stage of the Southern Fulmar population. Here, a few references. So we have basically 3 papers. So this is just appeared last year. So this is the more refined version. I would also highlight that Holger Metzler, who is a former PhD student of Carlos Sierra, has done some excellent work, in particular using probabilistic models. And that is described in his PhD thesis from 2020. And that's also serves as some nice introductory text to read if you're interested in transit times in general, with lots of references. So thank you very much for your attention. Looking forward to your questions.
Okay, great. Thank you very much. And we can thank the speaker with virtual claps. And yeah, we have some time for questions. If anybody has one, please feel free to ask.
I think Chris has a question.
I have a couple of questions. One is there any situation in which nonlinear effects are important?
Yeah, so this theory is of course for linear systems, and so for nonlinear systems you would have a matrix that depends. So you would have a situation. In some sense we covered in certain nonlinear situations here. So if this matrix, if this would depend on X, so you could basically have some transition rates which depend on the mass distribution. And then you would basically just plug in. So even if you have this for an autonomous system, so even if this B, you have basically a matrix B of X times X. So this would be a nonlinear system because the matrix depends on X. But then you can plug in your solution, and then you would basically have a non-autonomous system. And then even for autonomous nonlinear system, you could actually get some information by using this non-autonomous theory, because you fix on a specific solution. But for different solutions, you would get different behavior. But of course, in reality, you just have one solution. So that would be So this is so the nonlinear models normally look like that. And so as I said, so even if you're outside of equilibrium for an autonomous system which is nonlinear, then that would require such a non-autonomous analysis even for an autonomous system, and that can be done according to the lines that I have explained.
Second question is, I mean, this is sort of a little out in left field, I guess, but if I step back and thought about what would I expect in a talk about non-autonomous systems like this and transit times, I would have guessed that there would be a lot about Lyapunov exponent, but that doesn't seem to come up. Is that?
Yes, so this is something you can also calculate. I mean, this is basically a little bit swept under the rug here. So when I write here, basically this is globally attractive. So this basically means that there are some exponential rates, and these exponential rates are not given by these eigenvalues of these matrices P of t. So these are given by Lyapunov exponents. So the way the system would react to perturbation, so we are globally attractive here because we cannot really because for compartmental systems you cannot create mass. So mass comes from outside. So the only thing which can happen is, of course, that mass increases, but you would never have any positive Lyapunov exponent inside the system, which comes from this B of t, given the definition of a compartmental system. So the only way mass can be created by getting it from outside to the inside. But the Lyapunov exponents would just characterize how fast you would converge to the equilibrium solution, which is given by this X star here. And of course, you can calculate these things, but they are not, and they are related somehow. I mean, what we haven't really looked at is to what extent these Lyapunov exponents relate to these transit times. And I think you are quite right to ask this question, because there must be some relation, because yeah, you would think that yeah, maybe not in the way we have characterized it, because Lyapunov exponents don't depend on time. So Lyapunov exponents are basically integrated quantities. And so basically what I wanted to demonstrate here, that we have changes in time. So you can kind of compute the Lyapunov exponent. They have some meaning for the questions we discuss here, but they are just one number which corresponds to the whole time interval. So you have an application which is non-autonomous, and you get one Lyapunov exponent. Maybe you get one for forward time and one for backward time, which are different. First, you need to make sure that it converges, which is also not trivial, because here it doesn't mean necessarily when you have a non-autonomous system that you have a number which is given by Lyapunov. You could have a Lyapunov interval, for instance, in more general contexts. But if you have a Lyapunov exponent, there has somehow a meaning for these times. So basically, the inverse of the Lyapunov exponent would correspond to some time scale which we discuss here. But it would only be one number which corresponds to the more the asymptotic dynamics rather than a little bit finite time. So what we capture with this pullback transit time is a little bit finite time, because what is relevant for this time is what happens until time t, but the most relevant part is what happens close to time t in the past. So it doesn't really, of course, it goes in theory until minus infinity, but there's some kind of weighting, and this weighting comes also from the Lyapunov exponent somehow. So there's also a relationship with regard to that. So that's a very good question, and I think we have never really thought so clearly about how to express this relationship. But based on your question, I think it may be worth to explore this a little bit more rigorously rather than the few ideas I have just outlined.
Okay, thanks.
Okay.
Well, I have a very simple question. So I understand there's forward attraction and pullback attraction. How do you choose between the two?
You don't have to choose. I mean, either you have the one or the other, or you have both. So in this very simple application, because mass cannot really be created, we typically have, or typically, I mean, if we don't get some mass being trapped in some cycles and cannot escape, then we would get some decays, and this would decay towards the solution, and we have both forms of attraction. But you could have, I mean, for very simple examples, you can just have a one-dimensional non-autonomous differential equation, even linear. So you could just basically look at a x dot is equal, I cannot write now, unfortunately, because I don't have my iPad connected, but you could look at the differential equation x dot is equal to t times x. So basically t times x means for negative x, you would contract. Yeah. And then time becomes positive, you would suddenly expand. So you would get a pullback attractor, because pullback attractor covers time from minus infinity to a fixed time. So most of the time, for an infinite time interval, you would contract. And for a finite time interval, if you look at a time 10 or whatever, you would, on an interval of length 10, you would expand, but that doesn't dominate. So you would have a pullback attractor, but you would not have a forward attractor, because when you start somewhere, you only would on a finite interval, if you started for negative times, only on a finite interval, you would attract, but then you would on an infinite time interval, you would expand and repel, and you would not have an attractor. So this is a contrasting situation that can happen in non-autonomous systems. can have different behavior for the past and the future. And that's the reason why we have these two different types of attraction, which captures each of the two time lines, basically half lines.
Okay, thank you.
Okay. And I think Martin has some time constraints, so unless there's like a very quick question.
There's a few minutes time is fine if someone answers a question.
Okay.
I have not a question, but a short comment, which probably is known to most people. The formula for the transit times, or the transit times for certainly for the autonomous case, are very reminiscent of the corresponding formula for hitting times for Markov chains. Now we also use the transition matrix and apply it from the right to a unit vector, a vector of ones, and then you get your transition times, your hitting times until you hit another state. So it's really the same thing, it seems.
Yeah, it's the same thing. Yeah, so this is basically what Holger Metzler has done. But that's of course only for homogeneous Markov chains, which correspond to autonomous situation. So for inhomogeneous, yeah, so in his PhD thesis, he never looked really, he looked at some he didn't look at non-autonomous systems at all. So he defined some types of entropy also. That's what you see here. So Markov chains, H transit times and entropy. Mm-hmm. Yeah, but it's right. So these formulas are essentially the same. But for non-autonomous, we would need to look at inhomogeneous Markov chains, and that's not known in the literature, I think. Mm-hmm. But he looked also at higher order moments and so on. So this distribution. So the mean is of course the first moment. So he looked also at variance and third order, fourth order, and so on. So this is something he developed in his thesis also. Mm-hmm.
Okay. Any other last minute quick questions or comments? Okay, if not, we can thank our speaker. Thank you very much, Martin, for that wonderful talk. And of course, we'll post this to YouTube for those that couldn't make the adjusted time, and hope to see you all next week when Emmanuel will be speaking.
Thank you.
Thanks, Martin.
Thank
Bye-bye.
you so much. Thank you.